Hello. What about my audio? Is it clear? Hello.
Yes,
Oh,
it is
Zoom.
clear, sir. Yes, it is clear.
No, not Zoom. Me. This one. Google Meet.
Audio is clear.
Stop sharing. Yeah, stop sharing. Left, down, come down. Yeah, stop sharing. Okay, stop sharing. No, sir. On the left side.
Stop sharing.
Stop sharing. Yeah. Yes, sir. You can see that there is red button. Click on it.
Which? This one. This one.
Yeah, it says.
Okay. This one. No. Meet. I can't see Meet.
Wait, sir, 1 second. I'll try to remove from this call. I'll just stop it.
Okay.
Okay.
Hello. Shall I start it now? Hello.
Satish sir, can you hear me? Sir, can you hear me? Satish sir, can you hear me? He's not even seeing messages, sir. Please put it in the WhatsApp or call.
Hello. Shall I start the class now?
Yes, sir. You can start. We can't hear you. I mean, like he's not able to hear
Hello.
us. Yes, sir. It's no point. Please call him, sir. No, he can't hear us. He's not even seeing the chat box. So, please tell him to start the class. We can see. Ask him to go for slideshow. So, give me the phone when he speaks up.
Hello.
Sir, this is
sir.
Vinay.
Yes.
Go to the slideshow, sir.
Slideshow.
Please don't repeat.
Uh.
Just go slideshow. Slideshow. Yes, sir.
Yes.
So we can see you. We can hear you very well. You can go with normal class, sir. Okay.
I can start it now.
Yes, sir. You can start, and we will please check the chat box. If you have any doubts, I will fill you in if there is anything. Okay. Okay, sir. Thank you.
Okay, thank you. Good morning, all. I think I'm audible to all of you. So let us begin our class. So welcome to physics class. So let me start with electrostatics. In electricity, we will learn about charges which are at rest and also charges which are in motion. We can divide the branch electricity into two. The first one, in the first one, we will deal with the charges which are at rest. The second part, we will deal with the charges which are in motion. So before that, before our lesson, let us go back to the history. How electricity was discovered. This phenomenon was discovered by the famous philosopher Thales. He is from ancient Greece, around 600 BC. He found that when a piece of amber rubbed with cat fur could attract small pieces of straw and wood shavings. This happened only when this amber was rubbed with the fur made up of cat's hair. And Thales was able to find such another pairs of objects which will also attract tiny pieces of dry leaves, straw, wood shavings, etc. Actually, in Greek, the amber is known as electron. Because of that, later we called this phenomenon as electricity. So let us go to the term static electricity. What is electrification? So we can charge an object in different ways. So the process of giving charge to an uncharged object is called electrification. Normally, in the beginning, it was done by rubbing an object with another object. One example we have seen when amber was rubbed with a fur cloth, both this amber and the cloth which was used for rubbing got electric charge, and they were able to attract tiny pieces of objects. The amber is a resin. I think you are familiar with resins. So the charge achieved by amber was called as resinous. Now we can see how it happens. So this is a piece of ebonite and this is a piece of wool. Another two materials. If you rub ebonite with the wool, what happens? So electrons from the wool will be transferred. These are this yellow space are electrons. When you rub ebonite with wool, these electrons will be transferred from wool to the ebonite. This happens. So when wool loses electrons, let us assume initially there were 1,000 electrons in wool. Let us imagine that there are 1,000 electrons. It will definitely the number will be very large, but let us say there are 1,000 electrons initially in the wool. So due to rubbing, 100 electrons are transferred from here to ebonite. And one more thing I will say, there are 2,000 electrons were present in the ebonite. So when this 100 electrons are transferred from wool to ebonite, now what happened? What is the present scenario? The wool has got only 800 electrons. And the remaining 200 has gone to the ebonite. In a neutral atom, we have learned that the number of protons or number of positive charge and number of electrons are same. So when an atom loses an electron, it gains a positive charge. So what happens here? 200 electrons are shifted from wool. So the wool is now richer in the positive charge, which we call now. But what happened to ebonite? 100 electrons have joined ebonite. So the situation is now we have 2,100 electrons here. So now the ebonite is richer in negative charge and the wool is richer in positive charge. In that way, both these got charged. So what's the reason behind this charging? We know we need energy to transfer electrons from one body to another. Here what we have done, we have rubbed ebonite with the wool. So when you rub two objects together, friction will be developed. And because of friction, the electrons in the wool will get sufficient energy and they will go to the ebonite. So both of them got charged. Now we can see another pair. So in this way, we can say the ebonite becomes negatively charged and wool becomes positively charged. Now we can consider another two pairs. One is silk and the other one is glass. So when you rub glass with the silk, actually what happens is electrons are transferred from glass to the silk. So what will happen to glass? Of course, it becomes positively charged and the silk becomes negatively charged. So this is what happens when you rub an object with another object. So is it possible for us to create this type of electricity, static electricity, with the help of some other materials? You can easily do an experiment. If you have a plastic scale or a plastic pen or a plastic comb, rub this on your dry hair for some time. Rub it thoroughly. After that, you can see that this scale or the comb which was used for rubbing will be able to attract very tiny pieces of paper. That shows that our scale or the plastic comb is charged due to friction. And the charge occurred by this ebonite or wool, silk or glass rod have no ability to move from one place to another. So they will remain in the place where it was given. And that's why this electricity is called static electricity. And again, it is produced with the help of friction. So sometimes we will refer static electricity as frictional electricity. Okay, so again, Thales conducted some experiments. He found that two pieces of ebonite, which was rubbed with the wool, or the two pieces of our amber rubbed with the fur, they will be repelling each other. If you keep them together, they will be. If you keep them together, you can see that they will be moving away from each other. But if you use a cloth which was used for rubbing and the piece of ebonite, we can see that they will be attracting each other. So what does it indicate? These two pieces of ebonites which were rubbed with the wool are repelling each other, but the wool which was used for rubbing and the ebonite which was rubbed will be attracting each other. This clearly shows that the charge achieved by this ebonite and this cloth was two different types of charges. So we can conclude that there exist two types of charges. Earlier, these charges were named as, the charge achieved by amber was named as resinous because it is a resin, and the charge occurred by the cat fur is called a vitreous charge. This was the initial names given, resinous charge and vitreous charge. But later, the famous scientist Benjamin Franklin, who discovered that lightning is happening due to electricity, he only suggested the new names. Resinous was given the name negative and vitreous as positive. And thereafter, we are following the same name. So the negative charge is, the resinous is now known as negative and vitreous is now known as positive. Okay, now we can see, is there any other method for charging an object? So we can charge an object without even contact with a charged body or without even rubbing. Let us see how we can do it. By the presence of a charged object near another object, that object can gain charge. So we can charge an object without actual physical contact with another object. And this phenomenon is called charging by induction. So let us see how we can charge this object, which is mounted over an insulated stand, this sphere, how we can charge it with a positive charge. For that, what I have to do is, I will bring a negatively charged ebonite rod. We know how to give charge to ebonite rod. We can rub it with wool and it becomes negatively charged. So bring it very close to this sphere which is to be charged. Actually, they are not in contact. So what happens? We know in this object, there are large number of electrons and positive charge. So when this negatively charged ebonite rod is brought very close to it, the electrons on this side, the side which is very closer to the rod, will be repelled. We know like charges will repel each other. So these electrons will be repelled to the other side. So this side of this sphere will become negatively charged and this side will become positively charged. Now what we are going to do is, we will connect this end, which is negatively charged, to the earth with the help of a copper wire. We know that, we will call earth as an electron bank. Earth is referred as an electron bank because earth can supply any number of electrons to an object when it is connected together. And at the same time, it can absorb or receive any number of electrons. So we call earth as an electron bank. So I'm keeping this side of this object in contact with the earth, and this process is called actually earthing. So earthing is done. What happened? You can see what happened. So when we connect this one to earth, the electrons on this side will be moving through this copper wire to the earth. Now, remove the earth wire slowly. Then remove this negatively charged object. The positive charge will be distributed over the object. Now, this object is positively charged. So without any contact with the charged body, we are able to charge this object with positive charge. The same thing we can do with a negatively charged object. How can we make this object negatively charged? What is the main difference? In the beginning, we have brought a negatively charged object near this sphere. Now, if you bring a positively charged object near this sphere, we can charge the sphere with a negative charge. So you can try it. You just try how we can charge this object with a negative charge. Now, we are referring about positive and negative charges, and there's a unit for measuring the quantity of charge. So the SI unit of charge is coulomb. COULOM. It is called the coulomb. Coulomb is the SI unit of charge. Now, let us see what are the important properties of charges. Charges will exhibit certain properties. Mainly, we will learn about three properties of charges. First one is charges are additive. We can add charges like integers. We have two integers, positive 5 and positive 2. How we will add them? We can add them as positive 5 plus positive 2. It will be equal to positive 7. Similarly, if an object has positive 5 coulomb of charge, if another object has positive 2 coulomb of charge, the total charge can be positive 5 plus positive 2. Or if I give positive 5 coulomb charge to an object, again I am charging it with positive 2. Now the total charge will be positive 7. Now if the case is positive 5 and I'm giving 2 negative charge to this object, so what will be the new charge? It will be positive 5 plus negative 2. Definitely it will be positive 3. So just like integers, we are able to add the charges. And this property is called charges are additive, or we can add charges. We will go to the second property. It is called condensation. So there exists a basic charge. That is the importance of this condensation. And every object or any object has a charge, can have a charge, which is the integral multiple of a fundamental charge. So we can represent the charge Q on an object as N into E, where Q is the charge on a body and E is the fundamental charge and N is an integer. So the charge on any charged body can be expressed as Q is equal to N into E, or the charge is always an integral multiple of a fundamental or basic quantity. That fundamental quantity is actually, which is represented by E, it is the charge of an electron. So for us, the electron is considered as the fundamental charge. But actually, in modern physics, we know there are charges which has less charge than electron. But for our discussion, we are limiting to electrons. So the charge of an electron is 1.6 into 10 raised to negative 19 coulomb. This is the charge of an electron. And this quantum nature of charge was experimentally verified by a famous scientist. And that experiment is called Millikan's oil drop experiment. Note, this is a very important point. The quantum nature of charge was first demonstrated or illustrated or proved by Millikan's oil drop experiment And through this experiment, Millikan was able to find the charge of an electron. And he only determined the charge of the electron as 1.6 into 10 raised to negative 19 Coulomb. So this property is very, very important. You can do some small problems. Let an object, you can also work on it. Let an object has some 3 Coulomb charge. How many electrons are present in that object, or how many excess electrons are there to provide this 3 Coulomb charge? How do you solve it? You can consider this Q as 3 Coulomb, and E we have 1.6 into 10 raised to negative 19. So we can write Q is equal to, or 3, which is equal to N into 1.6 into 10 raised to negative 19. So we can find the value of N. How? We can just divide 3 with the 1.6 into 10 raised to negative 19. You will be able to calculate how much electrons are present in that object. Similarly, you can simply calculate how much or how many electrons are required to produce 1 Coulomb of charge. For that, what you have to do? In the place of Q, you use 1 Coulomb. So we will say 1 Coulomb is equal to N into E, from which you will be able to find the number of electrons which can produce 1 Coulomb of charge. Let me move to the third property. That is, charges are conserved. Charges are conserved. What do you mean by conservation of energy? And you have learned about conservation of energy, conservation of momentum. Everywhere we will say that the total momentum remains a constant, provided there is no external force acting on the system. Similarly, we will say the conservation of mechanical energy. The total mechanical energy of a system remains constant, provided certain conditions should be there. All the forces acting on it should be conservative. Similarly, if you consider an isolated system, the total charge in it remains constant. So this statement is known as the charge is conserved. In an isolated system, the total charge remains constant. What does it imply? We are not able to create a new charge, or we are not able to destroy a charge completely. Only we can transfer it from one body to another. So this property is also very important. Make a note of it. The 3 properties are: charges are additive, charges are quantized, and charges are conserved. Okay, now we can see how charges are shared between 2 objects when they are kept in contact with each other. So there was a question on our half-yearly exam. You may be remembering the 2 objects, how charges, and they are kept in contact with each other, how these charges are distributed. So let us see. Let us consider an object. First, this one has got 18 Coulomb of charge, and this object has no charge. It has 0 charge. Now, if we keep them in contact with each other, actually what happens is that this total charge of 18 Coulomb is shared between these 2 in the ratio of their surface area. So the charges will be shared between these 2 objects in the ratio of their surface area. In this case, these areas are in the ratio 1:2. So let us imagine this object, I am naming it as A. This and this one as B. Their surface areas are in the ratio 1:2. So I'm going to keep them in contact with each other. So this charge will be distributed among them. How? Can anybody tell me the answer or put answer in the chat box? How the charges will be distributed among these 2? Can anybody tell me an answer? How this 18 Coulomb will be distributed in between these 2 charges? Okay, I think you may have some difficulties in typing it. Not by induction, I'm keeping them in contact with each other, not induction. I kept both of them in contact with each other. Very good. I got an answer from Banwat P. 6 Coulomb and 12 Coulomb. Why it is 6 and 12? Why 18 is divided as 6 and 12 because the areas are in the ratio 1:2. So we can divide 18 only as 6 and 12. 6 coulomb is to 12 coulomb will be 1:2. So we will be dealing some problems with this in the afternoon session. Okay. So always remember that when a charged body or when two charged bodies are kept in contact with each other, the charge will be shared between them equally in the ratio of their areas. Now we are going to learn the first law in electrostatics, and we are familiar with this name Coulomb. We used the unit of charge, the name Coulomb as the unit of charge. Why? Because he only was able to calculate the quantity of or the force between two charges. So let us see the statement. The force between this is Coulomb. The force between 2 point charges is directly proportional to the product of the charges and inversely proportional to the square of the distance between them. Mathematically, I can write this. For I am considering one charge. This is Q1. This is another charge Q2. Let us separate them with a distance R. So Q1 is the charge on the first object. Q2 is the charge on the second, and they are separated by a distance R apart. So let us see how we can apply this one, write this law mathematically. So this is written as the force F is directly proportional to the product of the charges. The charges are Q1 and Q2. The magnitudes of the charges are Q1 and Q2. So F is proportional to Q1, Q2. At the same time, it is inversely proportional to R square. Or F is proportional to Q1, Q2 by R square. We can introduce a constant of proportionality here. When A is directly proportional to B, normally we will say A is equal to a constant into B. So this proportionality symbol can be replaced by equal symbol by multiplying with a constant. That constant is called K. So F is equal to K into Q1, Q2 by R square. So this equation gives the magnitude of the force between two charges. Now, how will you distinguish between attractive force and repulsive force based on this equation? So if Q1 and Q2, if both Q1 and Q2 are positive, what will be the product Q1, Q2? The product Q1, Q2 will be definitely a positive number. Again, let us say if Q1 and Q2 are negative. So what happens? Again, the product of two negative numbers will be a positive number. So if Q1 and Q2 are positive, their product will be positive. If Q1 and Q2 are negative, their product will be again positive. So a positive, if you get the product of Q1 and Q2 as positive, it refers to similar charges. So the force will be repulsive. Now, if Q1 is positive and Q2 is negative, what will be the situation? Q1 is positive and Q2 is negative. What happens? Q1, Q2 will be negative and it will be definitely attractive. So if Q1, Q2 product of two charges is positive, we can say the force between them will be repulsive. And if the product of two charges is negative, we can say the force between them will be attractive. Now, how to find the value of the constant K? I told that K is a proportionality constant, but it is not a universal constant. K is not constant always. It depends upon the medium in which the two charges are kept. K depend upon the medium. If we keep these charges in aero vacuum, the value of K is equal to 1 by 4 pi epsilon 0, where this epsilon 0 is called the permittivity of air or free space. This constant epsilon 0 is called the permittivity of air or free space. If we consider any other medium than air, this constant is not written as epsilon 0, it will be written as epsilon. So for any other medium other than air, we will say the constant K is equal to 1 by 4 pi epsilon, and epsilon is called the permittivity of that medium. And it is different for different media. Okay. Now, we want to express this expression in a slightly different way. Always we have to relate with epsilon 0. How is it possible? So if you consider the permittivity of free space as the reference value, then the ratio of permittivity of a medium to the permittivity of free space. That means I'm considering a medium whose permittivity is epsilon, and I'm considering the permittivity of air. And if I calculate this ratio, sigma by epsilon 0, sorry, epsilon by epsilon 0, this ratio will give you an idea about the permittivity of this medium. It is, if this ratio is 1, I will say this medium has a permittivity equal to that of air. And if this ratio is 2, I can say this medium is having a permittivity which is double that of air or free space. So in that way, we can have a comparison, and this ratio is known as the relative permittivity denoted by epsilon r. So epsilon r is epsilon by epsilon 0, or epsilon is equal to epsilon 0 into epsilon r. So generally, we will write the force between 2 point charges. The magnitude is given by 1 by 4 pi, what you can write epsilon r, epsilon 0, q1, q2 divided by r square. This is the normal way of representing the force between two charges when they are kept in a medium whose relative permittivity is epsilon r. You can write this expression as 1 by 4 pi epsilon, nothing is wrong in it. But normally, when you solve numericals, they will give only the epsilon r. So we will go for epsilon by multiplying epsilon 0 and epsilon r. That's why. Now, since force is a vector, how to express this Coulomb's law in vector form? That is very important. Sometimes this can be asked as a 1-mark question. Express or write Coulomb's law in vector form. So for that, I am considering a unit vector connecting Q1 and Q2. So this unit vector R12 or R12 cap is a unit vector from Q1 to Q2. So I can write the force between these two charges 1 and 2. It is written as F12 is equal to K into Q1 Q2 by R12 square multiplied with R12 cap. We know if you multiply any number with a unit vector A, its magnitude will be NA and direction will be same as A cap if N is a positive number. And the direction will be opposite to it if N is a negative number. So this is the vector representation of Coulomb's law. It can be written in another way. We know that R12 is equal to R12 cap is any vector. We can find the any vector in the we can find a unit vector in the direction of any given vector by dividing that vector with its magnitude. You have learned it in the 11th class. A cap is equal to vector A divided by the magnitude of vector A. So R12 will be equal to R12 cap. The unit vector in the direction of R12 is equal to vector R12 divided by R12, or we can write it as F12 is equal to K into Q1 Q2 by R12 cube multiplied with vector R12. Don't think that it is Coulomb's inverse cube law. It is not Coulomb's inverse cube law. It is Coulomb's inverse square law only, because the force is inversely proportional to R12 square. You may have a doubt why cube is written here. Here we have written R12. Its magnitude also has a unit. So these two will be cancelling and you will get it as R12 square. The magnitude will remain same in these two cases. You can learn any one of these two. No need to learn both. Whichever is easier for you, you can learn it. Okay. Now, the value of epsilon 0 is 8.8542 into 10 raised to negative 12. The unit is Coulomb raised to negative 2, Newton inverse meter raised to negative 2. And the 1 by 4 pi epsilon 0 is precisely 9 into 10 raised to 9. So when you are doing numericals, when we want to substitute for this 1 by 4 pi epsilon 0 together, you can simply write it as 9 into 10 raised to 9. No need to substitute here 8.854, then 3.14 and do all those calculations. You can just remember this value. 1 by 4 pi epsilon 0 is 9 into 10 raised to 9. Okay, now we are in a position to define 1 coulomb of charge. So how do you define 1 coulomb of charge? I have not defined 1 coulomb charge. I simply told you that the unit of charge is coulomb. So this coulomb is defined in terms of Coulomb's inverse square law. 1 coulomb is the charge which experiences a repulsive force of 9 into 10 raised to 9 Newton when it is kept at a distance of 1 meter from an equal and similar charge in air or free space. So if I have a charge here, let it be Q, and it is kept from another similar charge Q, and the separation between them is 1 meter, and this is done in air. I'm measuring the force between these two charges, and I found that it is equal to 9 into 10 raised to 9 Newton. So, or it implies that both these Qs are of 1 coulomb. That is the meaning. 1 coulomb is that charge which experiences a repulsive force of 9 into 10 raised to 9 Newton when it is kept at a distance of 1 meter in air from a equal and similar charge. Similarly, we can find the equation for relative permittivity. So I will give you the expression for the force between two charges in air first. You just calculate and find this definition. It is 1 by 4 pi epsilon 0. Two charges are Q1 and Q2 separated by a distance of R. When I keep these two charges, the same two charges in another medium, and I found that the force is 1 by 4 pi epsilon 0 epsilon R Q1 Q2 by R square. Just find this ratio and you will be able to define this epsilon R. So it is given to you as a homework. You please do this and define the relative permittivity from these two simple equations. So these are the two definitions which we can get from Coulomb's inverse square. Now, we know what is electric field. Everybody defines electric field as a region around a charge where it can apply a force on another charge. So we learned that we learned Coulomb's inverse square law. It says the force between two charges is inversely proportional to the square of the distance between them. The force F is inversely proportional to the square of the distance between them. So at what distance of separation between two charges, this force becomes 0? Can anybody tell me? At what distance this charges will become 0? What should be the distance of separation between two charges to get 0 force? That is my question. Okay. No answer so far. Okay, let it be. We will see later. Now, how will we define electric field as a physical quantity? How we can measure the strength of the electric field near a charge or around a charge at different points? For that, what we are doing is we will keep a charge capital Q in at a distance from a given charge, and we will calculate what is the force experienced by that charge. Then we can standardize it. So how we can standardize? We will make that charge as 1 coulomb. So the electric field or the strength of the electric field or the electric field intensity at a point is defined in an electric field is defined as the force experienced by a unit positive charge kept that point. That's the definition of electric. If I want to calculate the electric field intensity at this point, if this is an electric field, I want to find the electric field intensity at this point. What I have to do? I have to keep 1 coulomb positive charge, which is called a test charge, at this point, and I will try to find what is the force experienced by this charge. So that will give you an idea about how much strong is the electric field at this point. So if when I go and keep this same charge at this point, if I keep the same charge at this point, the force may be different. This Q, when I keep this positive 1 coulomb charge at this point, it may experience a sometimes lesser force or sometimes a greater force. So we can have a comparison where the force is more, and we will say that the strength or the electric field intensity is more at that point. So this is the concept of electric field intensity. But normally, we won't say electric field intensity always. We will simply say electric field. So we can say the electric field at a point is the force experienced by a unit positive charge kept at that point. So by saying electric field, actually what we mean, electric field intensity or the intensity of electric field. So let us try to find an expression for it. So a charge, capital Q, is kept at a point. And I measured the force experienced by it. A capital Q charge is kept at a point, and I found that it experienced a force, capital letter F. So Q coulomb of charge experienced a force of F. So what's the force experienced by 1 coulomb? Definitely, for Q coulomb, there are F forces. So 1 coulomb, the force will be F divided by Q. So what's the force experienced by 1 coulomb positive charge called? It is called the electric field intensity or electric field, and it is denoted by E. So electric field is equal to F divided by Q, where F is the force experienced by the charge Q. What will be the SI unit of electric field intensity then? So in vector form, we can write it as vector E is equal to vector F by Q. So we can conclude that since force is a vector, charge is a scalar, E also is a vector. So electric field intensity is a vector. It has got both magnitude and direction. What will be the SI unit of electric field intensity? We know the force is measured in Newton. Force is measured in Newton and charge is measured in Coulomb. So Newton per Coulomb is the SI unit of electric field. We have one more unit that we will learn in the next chapter. It will be volt per meter. You are not familiar with the volt. I think all of you have learned it. Volt is the unit of potential difference. So this unit also can be used for expressing electric field, either Newton per Coulomb or volt per meter. Okay. Now, how to find the force experienced by a charge in an electric field? So I have kept a charge Q in an electric field E. So what is the force experienced by it? We learned electric field E is the force experienced by unit charge or 1 coulomb charge. Electric field intensity at a point is E. The meaning is 1 coulomb charge will experience this much force. So if I keep Q coulomb charge there, what will be the force? Positive 1 coulomb charge experiences a force E. So Q coulomb charge will experience a force equal to 1 coulomb charge, E force. So Q coulomb charge will experience a force equal to QE. So I can write it as F is equal to Q into E. Now, what happens when this Q is positive or negative? What will be the direction of this force? If Q is a positive integer, vector F will be positive Q into vector E, which means F and E are in the same direction. So a positive charge experiences a force in the electric field in the same direction of electric field. Now, if Q goes negative, then what happens? This F will be equal to negative Q into E. What is the significance of negative symbol in vector notation? The negative sign shows that this force F has a direction which is opposite to the direction of E. So it is very clear that a positive charge will experience a force in an electric field in the same direction of the electric field, and a negative charge will experience a force in the opposite direction of the electric field. This is also a very important point. Sometimes you may be asked to find the direction of the force experienced by charges in certain region. So this will help you to find the direction. The positive charge will experience a force in the same direction of electric field, and the negative charge will experience a force in the opposite direction of electric field. Now we are going to derive the expression for the electric field at a point which is at a distance from a charge. So we have this is the origin of the coordinate system. I have the origin O, and I have kept a charge Q here. Now let me consider a point P, which is at a distance R from this O, and I am keeping a charge Q here. What I want is, I want to find the electric field at this particular point P. What is the electric field intensity or electric field at this point P due to this charge Q? What is the procedure? So let me find what is the force experienced by this Q. What will be the force experienced by the capital Q charge there? By using Coulomb's law, I can find F is equal to 1 by 4 pi epsilon 0 q into small q divided by r square if the distance between these two is r. This is the magnitude. So this is the force experienced by q units of charge. So what's the force experienced by is 1 coulomb charge? It is called the electric field. So electric field, q coulomb experiences F force. So what's the force experienced by unit charge? F by q. So when you divide this with the q and q will cancel and you will get the expression as 1 by 4 pi epsilon 0 q divided by r square. Or the electric field at this point P, which is at a distance r from a stationary charge q is equal to 1 by 4 pi epsilon 0 q by r square. Okay. In vector form, again, we can write it as vector E is equal to k is 1 by 4 pi epsilon 0 q into q by r square multiplied by r cap or vector r by r. This is the vector representation. Okay, again, we can say what will be the electric field at a point which is at an infinite distance. If r becomes infinity, so what is the expression for electric field? E is equal to 1 by 4 pi epsilon 0 1 by 4 pi epsilon 0 q by r square. This r becomes infinity. So what 1 by infinity is referred as 0. So this charge will experience 0 force there. So the electric field due to a point charge will vanish only at infinite distance from the charge. Again, if you separate two charges so that both of them are at infinity, then only the force between the charges will become 0. Now, there's a graph which shows the variation of E with the R. How electric field intensity varies with the R. We know these two are inversely proportional. The graph for inversely proportional will be like this. It starts from here. It goes and it goes to infinity. And this one, these two will be meeting at infinity. These two also will be meeting at infinity. So this is the graph which shows the variation of electric field with the distance from a point charge. That line is not there. Okay. This part is not there. It's due to some movement of the mouse, it happens. Okay. I will change it. It will be like this. This is the graph which shows the variation of electric field with the distance. Now, how to represent electric field symbolically? How we can represent the electric field around a point charge? So we will do it with some imaginary lines around a charge. So we can represent the electric field around a charge with some imaginary lines. So the so this is a positive charge, and if I keep a unit positive charge here, or if I keep a unit positive charge here, very close to it, so unit positive charge, it experiences a repulsive force. So it will be moving along this direction. If I keep it here, definitely it will be moving along this direction. If I keep it here, there will be a repulsive force along the line joining the two. So it will be moving in this direction. Similarly, wherever I keep, this force will be radially outwards, or this charge will be moving in the radially outward direction. So we will call the electric field line as a path along which a unit positive charge will move in an electric field. The path traced by a unit positive charge in an electric field is called electric field lines. So with the help of this electric field lines, we are able to represent the electric field. Now, in the case of a positive, isolated positive charge, this is the direction of the electric field, or the electric field line pattern will be like this. But around a unit, an isolated negative charge, the pattern of electric field lines will be like this. This arrow shows in which direction this charge will move. Here they are moving away from the positive charge. Here they are moving towards the negative charge. Now, if we have two positive and negative charges together, this will be the pattern of electric field lines. Again, if you have two positive charges, you can see this will be the pattern of electric field lines around it. So these are different patterns. So what is meant by an uniform electric field? What is the meaning of the word uniform? Uniform means which is similar or equal in every aspect. So an electric field, if a region, if you have a region and if you check the electric field at all points in that region, if they have the same magnitude and the same direction, if they have equal magnitude and same direction at all points, such a field is called a uniform electric field, which has the same magnitude of electric field and the electric field will be having the same direction. How to represent such a uniform electric field? A uniform electric field is normally represented like this. Parallel straight lines with these arrows. These arrows will show the direction of the electric field. So the electric field is normally directed from the positive charge to the negative. So if you release a positive unit positive charge at a positive charge, so the unit positive charge will move from the positive charge to the towards the negative charge. So we will say the direction of electric field is from positive to the negative charge. Now we have to see what are the important properties of electric field lines. Normally the electric field lines will start from a positive charge and end in a negative charge. The electric field lines will start from a positive charge and end in a negative charge. They have a beginning and they have an end. So the electric field lines start from a positive charge and end in a negative charge. They are not closed loops. We cannot see an electric field pattern like this. It is not possible for us to have an electric field configuration like this, starting from the same point and ending at the same point. Why it is not possible? You know, you can't have a positive and negative. It should start from a positive charge and it should end in a negative charge. But it is not possible for us to keep a positive and negative charge at the same point. They will collapse each other. Now, they are continuous curves. So they start from a point and it will go up to infinity. There is no gap in between. The electric field line cannot have a gap in between. It will be continuous. And how to find the direction of the electric field at a point? So just draw a tangent. If it is a straight line, directly we can find. If it is in the form of a curved line like this, we will be able to draw a tangent at that point, and that tangent will give you the direction of the electric field. So we can find the direction of the electric field at a particular point by drawing the tangent to the electric field line. Now, the electric field has got one more important property. They always come out of a charged object normal to its surface, and they will go and merge or emanate into an object normal to that surface. So whatever may be the surface from which they are coming out or they are merging into, it will be normal. Now, most important property, two electric field lines will never intersect. Electric field lines cannot intersect each other. They will never intersect. We will see why. Similarly, that I will explain later. Then there is one more property. They can contract lengthwise and apply lateral pressure. So that I will explain here. So this is a positive charge. Normally, we know when you release a positive charge here, it should move like this. But why it is bending and going to the negative charge when there is a negative charge nearby? So they can contract lengthwise. Instead of going to infinity, they will start from positive charge and they will go and end at the negative charge. Here what happens? Two positive charges are here. Instead of going directly, it is moving like this. They are bending sideways. So this explains why the two will attract and these two will repel. Now let us see what happens if two electric field lines intersect each other. So this is one electric field. This one is another electric field. And they are intersecting at this point. I have marked it. So they are intersecting at this point. If they intersect, what will happen? At this point, if they are intersecting, what will be the case? So this is a curve. I can draw a normal here. So this normal, sorry, I can draw a tangent here. This tangent will give you the direction of the electric field at this point. Let me call that point as P. This is P. I've drawn a tangent here, and this is the electric field. This is the direction of the electric field. Again, another line is passing through the same point, but in another direction. So I can draw a normal here. So E2 will be the direction of the electric field at this point P. Is it possible? Is it possible for a physical quantity to have two directions at the same point? Is it possible or not? It is never possible. So a vector which can have only one direction at a particular point P. So this is an impossible thing. Electric field cannot have two directions at the same point. So what should happen there? Electric field will be having two directions at a point if they intersect. But electric field cannot have two directions at a point. That is, what does it mean? Electric field lines can never intersect. So if it happens, there may be two directions for the electric field, but it is impossible. So it will not happen. Electric field lines will never intersect. I have some figures, and which of these figures represent the correct configuration of the electric field, which obeys all the properties of the electric field. What about A? Is it an electric field? These blue lines, are they representing electric field lines? Or you have to check whether all the properties of the electric fields are obeyed. It is positively charged, and we know that electric field line should start from a positive charge, and I think all the arrows are outwards. No problem. But is any other violation? Can you tell me? Okay. Just to check the property where when the electric field comes out of a surface, it should be normal to the surface. What about in this case? Is it a normal? Is it a normal? In many cases, they are not normals. Here you can see it is almost a tangent. So electric field can never tangential to a particular surface from which it is coming out. It should be like this. So this is not a possible configuration. We can discard it. What about this? The second one, I think it is more simple. You can see a positive charge here, and electric field lines are coming and going to the negative charge. Now what happens next? The electric field is starting, again the field line is starting from the negative and ending at the positive, which is not possible. We know electric field lines can start from a positively charged object and it must end on a negatively charged. It cannot come out from a negatively charged. Again, here it is going towards into a positively charged, positive charge. So this one also not correct. What about the third one? C. Is it possible? Okay. Continuous curves are absent, but with this arrow shows that they are continuously moving. Okay. Now, is it possible for this configuration? If you observe very carefully, you can see that everywhere it is normal to the surface. And here they are bending on both sides and they are not intersecting. The direction is from the positively charged object. Here also, everywhere these arrows are outside. So this is a possible field. This one is possible. So what is wrong with this? At a glance, you can see. What is wrong with this? How many properties are violated here? All are positive charges, but it is moving from positive to positive. That is not possible. More than that, what you can see in this region? One more violation. What you can see in this region? These field lines are intersecting, which is also not possible. They will never intersect. So this is not a correct configuration. Very, very good. I got answer from one viewer. So what is wrong with this case? Everywhere almost it is normal and all are negatively charged. Here it is positively charged. They are moving out from positive to negative. But observe this area. you can see two closed paths. This one and this one. So we learned a property where electric field lines can never be in the form of closed loop. So this is also not a configuration. So out of these five figures, only the figure C represent the correct pattern of electric field lines. All others are not representing any electric field line. You can expect such questions in your exam. So if you learn all the properties, you will be you can easily determine which is the correct configuration or which is the wrong configuration. Now let us see what is meant by superposition principle. Okay, if you have a large number of charges, for example, this is the origin, and I have a charge Q1 located at this point, which is at a distance R1 from the origin. And we have another charge Q2, which is located at a distance R2 from O, and another charge Q3. Now, this definitely, I want to find the total force experienced by the charge Q1. What is the force experienced by the charge Q1 that I want to calculate? And there are two other charges, Q2 and Q3, and both of them are applying, this Q2 is applying a force on Q1, and Q3 is also applying a force on Q1. So what will be the total force? We can calculate the force between Q2 and Q3 by using Coulomb's law. I have written here, F12 is 1 by 4 pi epsilon 0, Q1, Q2 by R12 square with this R12 cap, because force is a vector. In vector form, it is written like that. Again, I have put the vector symbol here and here also. Then I can find the force experienced by this Q1 due to the charge Q2. Q2 we have here, Q2 is here, and this is Q1. So distance between them is R13. Again, I can use the Coulomb's inverse square law, and I can say F vector of 13 is equal to 1 by 4 pi epsilon 0, Q1, Q2 by R13 square into R cap 13. Okay, if I keep a unit, let us consider all these charges as positive charges. This is a positive charge, this is a positive charge, this one also is a positive charge. Let us imagine like that. So what will be the direction of the repulsive force F12? Both are positive, and that force will be acting along the line joining the two charges. So it will be directed in this direction. This is the direction of F12. So this represents vector F12, and this represents vector F13. So now we have two forces acting at the same point, one along this direction and one along this direction. If when I have given some values and I found that this is 10 Newton, I'm giving an example. Simply I say that this is a 10 Newton force, this is a 5 Newton force. How to find the total force? We cannot directly add them. We cannot add this 10 and 5 directly. I cannot write 10 plus 5. Why? Because they are acting in different directions. They are not mere numbers. They are vectors. So how to find the sum of two vectors? It is not normally called as sum. It is called resultant of two vectors. So we have to find the resultant of these 10 Newton force and 5 Newton force. For that, we should know one more thing. This angle between these two. If this is theta, we can use the formula we have learned last year. The resultant of two vectors has a magnitude. If they are A and B, S square plus B square plus 2AB cos theta. If theta is the angle between them. This formula we can use where A is 5 Newton, B is 10 Newton, and theta is the angle between them. For simply we can consider, or we can apply the parallelogram law of vectors here. These two are the sides of a parallelogram. So we can complete the parallelogram and we can draw the the diagonal passing through the common point. So this diagonal will give you the resultant force. So here it is represented in that way. But we can find the magnitude by using this formula, and we can find the direction by either detecting this angle, which is called alpha, or this angle, which is called beta. How do you find this alpha and beta? We know the force F13, we know the force F12. If this is F12 and this is F13, this represent the force F F12, and this represent the force F13. These two parallelograms, these two are equal. So if you find tan alpha, it will be F13 by F12. If this angle is alpha, if I calculate tan alpha, it will be F13 by F12. And from that, we are able to find the direction, or the resultant force will make an this much angle with this force. In that way, you can say. And if you have some other forces here, again, we have to find the vector sum of all the forces. If one more charge is kept at this point, if we have one more charge here, if this distribution has one more charge, let us say Q4 here, again, this also has an influence on this. There will be a force like this, and you can calculate that force, and again, you can find the resultant. So two vectors resultant, we can say that with the resultant and the third one, we can see the resultant again. In that way, we can find the total force. So if there are a number of forces F12, F13, etc., F1n, if there are n charges, so the total force will be the vector sum of all these forces, not simply the sum of the magnitude of the forces. You have to consider them as vectors, and you should find the resultant. We'll be doing some problems in the afternoon based on this. Now we are going to the new topic, which is called an electric dipole. So an electric dipole is two equal and opposite charges separated by a finite small distance. So this is a positive charge Q. This is a negative charge Q. Both of them have the same magnitude, and they are represented separated by a very small distance. This distance is normally denoted by 2a. Why are we going for 2a? That you will understand when we derive the expression for the electric field. So positive Q and negative Q are separated by a distance of 2a. Now this configuration is called an electric dipole. So we can find some electric dipoles in nature. You might have learned about ammonia molecule in chemistry, NH3. It's a dipole. It's a natural dipole. Why? NH3. It has a lone pair of electrons somewhere away. So the remaining part will have a positive charge, and this one have a negative charge. So these two are separated by a finite distance. So this ammonia molecule will be behaving like a electric dipole. So what is an electric dipole? Two equal and opposite charges separated by a finite small distance. And the distance between the charges is denoted by 2a. Now there is a characteristic of this electric dipole. The properties of the dielectrics are explained not simply on the basis of these charges and this distance. Both the terms are important. So we will consider a new term which is called the electric dipole moment. So it is a characteristic of an electric dipole moment. And it is defined as the product of one of the charges and the separation between the charges. And it is a vector. So it is written as vector P is equal to Q, one of the charges, into 2a, which is considered as a vector. So what is the direction of this dipole moment? It is very, very important. The dipole moment is directed from in this way. So it is directed from the negative to the positive. So remember that electric dipole moment is a vector. Its direction is from negative charge to the positive charge. So what's the direction of electric field? Don't confuse in between. The electric field is directed from positive to negative, but electric dipole moment is directed from negative to positive. What will be the SI unit of dipole moment? Again, Q is the charge measured in coulomb, and distance is measured in dipole distance. The distance between the two charges is measured in meter. In SI unit is meter. So it will be coulomb meter. Coulomb meter is the SI unit of electric dipole. Now, these problems we will see later. Now we will go in details about the electric dipoles. Okay. Now we are going to calculate the electric field due to a dipole. So, sorry, one thing is not visible here. Let me just rearrange it. Okay. So this is a negative charge. This one is a positive charge. Let them name let it be negative Q, and this one is positive Q. And the distance between them is normally we will call it as 2A. This is 2A. Now 2A is called the dipole length, and positive Q and negative Q will be representing the two charges. Also, what is the direction of dipole moment in this case? Vector P is directed from negative to the positive. It will be acting in this direction. So when we go to find the electric field at a point around this, we will give importance to two lines. One is the line joining the two charges. So this line joins the centers of the two charges, and this line is called the axial line. We will call this line as axial line of the axial line. AXIA. And the perpendicular bisector of this line is called the equatorial line. It is called the equatorial line. So we will be deriving the electric field at a point on the axial line and also at a point on the equatorial line. So we have this derivation is actually very important nowadays for our CBSE board exams. Derivations, very limited number of derivations are asked in the recent years, but this is a very important derivation, and let us deal with it. How to find the electric field at a point on the axial line and also on the equatorial line. For that, I'm considering this dipole. This is negative Q and this is positive Q. This is the center and the distance between them is 2A, and this line is called the axial line. So let me consider a point somewhere here on it. And this is the point P. And I want to find the electric field at this particular point due to the combination. Due to this dipole, I'm going to find the electric field at P due to the dipole. Oh, somebody is saying my presentation is not coming. Is it visible to you now? Can anybody please respond? Are you able to see the presentation? Okay, okay. Somebody says it is yes. Somebody says it is no. I think who are not able to see this? Those who are watching in Zoom or YouTube, can you please tell me? So Ganesh told it is not visible. The problem is displayed. This dipole is not seen. Are you using Zoom or will you please tell me which in which streaming you are seeing? Either Zoom or YouTube. Those who are not able to see. Okay. Okay, I will share it. It will be visible to you. I think this one will be visible now. Is it? Is it visible to all of you now? Is this figure dipole is visible to all of you now? Okay, I am streaming through two different platforms. That's why it happened. I am very sorry for the inconvenience caused. I think, do you want to see the previous slide again? It's just, I have given a dipole and I have explained what is dipole moment and what is its SI unit. Okay, now I think it is visible to all of you. Okay, so this is a negative Q charge. This is a positive Q charge. And we have a line which joins the centers of these two charges. And it is called the axial line. Now I am considering the perpendicular bisector of this axial line, that is called the equatorial line. Now let us try to find the electric field at a point both on the axial line and also on the equatorial line. Let us try to derive the expression for that. Okay. So this is a dipole again. This is a point P. Let me refer the. Okay, I think it is visible to everybody now. Okay. Now this point P is at a distance R from the center of the dipole. The distance of this is the center O of the dipole. And from here, the point P is at a distance R. And we know the dipole length is 2A. So this part will be A. And this part will be again A. Because it is a perpendicular bisector. Is it clear? So this distance will be A and this distance will be A. Now, I'm going to place a unit positive charge here. 1 coulomb positive charge is placed at P. And how to find the electric field? We have to find the resultant force experienced by the 1 coulomb positive charge kept at P. So that we are going to calculate. For that, we have to find the force experienced by P due to this positive charge and also the force experienced by P due to this negative charge. So we have to find the total force. Remember, forces are vectors. So we have to find the resultant of the force due to the positive Q and also the force due to the negative Q. Okay, we will move to the next slide. This is the situation. So I'm going to write the expression. I think it is visible. This is negative Q. This is positive Q. And this is the point P. Now, the distance between the center of the dipole and center of the dipole and the point P is R. So first of all, let me write what is the force due to the positive charge. It will be, I'm not going to write the entire constants 1 by 4 pi epsilon 0. Just to simplify it, I'm writing K into what it will be positive Q into positive 1 because I'm keeping 1 coulomb charge here. 1 coulomb charge is kept there divided by the distance between this positive charge and the point P have to be considered because this point P is at a distance, this much distance from the positive charge. So how to find the distance? I want this much distance actually. So this total distance is R, this much is R, this much is A. So how to find the distance between the positive charge and the point P which we are considering? From here, the distance is, total distance is R. And from the positive charge, from the center, the positive charge is at a distance A. So distance between these two will be equal to, definitely equal to R minus A. R minus A and the square of it. So F positive Q will be K into Q into 1 divided by R minus A the whole square. The total distance is R. This much distance is A. So this distance will be equal to R minus. Similarly, and in which direction it is acting? How to find the direction of that force? So that force will be along this direction. And we know the dipole moment will be in the direction negative to positive. The dipole moment is acting from this in this way. So I can consider the unit vector in that direction. That will be P cap. So P cap will be directed from negative Q to positive. This is the direction of P cap. So in terms of P cap, how will you write the expression for the force? P cap is a unit vector. So this can be written as multiplying it with the P cap. Both are in the same direction. This is the direction of P cap and this is the direction of force due to the positive charge. Now let us write the expression for the force due to the negative charge. That is F negative Q. It will be equal to K into what it will be? Again, magnitude is k into positive of k into 1 divided by r minus a the whole square. Same, sorry, not r minus a. This distance will be r plus a the whole square. Why? This distance is r. This one is a. So total distance will be r plus a the whole square. And what will be the direction of this force? This is a negative charge. This is positive charge. So it will be attracting. This is the direction of the F negative Q. So with the in vector, we will denote it with a P with a negative cap multiplied by P negative cap. Now we can find the resultant force. That will be the electric field there. It will be equal to K into 1 by K into Q divided by R minus A the whole square minus K into Q divided by R plus A the whole square. Okay. So by evaluating these two, you will be able to find the total force. I think we can do these calculations. This is equal to what you will get. K is a constant, Q is a constant. We can take them out. Both are common. So 1 by R minus A the whole square minus 1 by R plus A the whole square. Now we can find the LCM and we can do some calculations, and finally you can arrive at the expression. You can derive it. The expression will be, final result will be, when you introduce and P into it, the electric field will be 1 by K is 1 by 4 pi epsilon 0 into 2P by R square minus A square the whole square into P cap. It will be the expression for the total electric field along the axial line. Is the writing is not visible? Again, somebody is complaining, writing is not visible. Can anybody tell me, please, is it visible or not? Whatever I am writing on the slide. Okay. Thank you. Now, let us consider what will happen to the electric field at a point on the equatorial line. How to derive the expression for that. So, I will explain it. So, this is the equatorial line. We have a point charge here. This is negative Q charge. This is positive Q charge. This distance is A. This is the center. And this will be equal to O. This distance will be A. Now, let us consider point P, which is at a distance R from the center. So, this is the distance of the point P, which we are considering from the center. Now, here I am keeping a unit positive charge. Positive 1 coulomb charge is kept here. Positive 1 coulomb charge is kept here. Now, I want to find the force experienced by this positive 1 coulomb charge. For that, I have to find the force due to this negative charge and also the force due to the positive charge. Then find the resultant of these two charges. So let us see how to find it. And when positive 1 coulomb charge is kept here, and what about this distance? So this is a right triangle. And this is a hypotenuse. It will be equal to square root of R square plus A square. So this distance will be square root of R square plus A square. Similarly, this one also will be square root of R square plus A square. So these two sides will have the same length, or the point P will be equidistant from both positive charge and the negative charge. Now we can find the magnitude of the forces. The force due to the positive charge will be 1 by 4 pi epsilon 0 into Q into 1 by square of this distance. That will be R square plus A square. The distance is square root of R square plus A square. Its square will be Q by R square plus A square. And what is the force due to the negative charge again? What magnitude is 1 here, magnitude is Q here. So product will be Q and the same distance. The distance between them is root of R square plus A square. So E negative Q will be 1 by 4 pi epsilon 0 R square plus A square again. But there is a difference. What is the difference? This is a positive charge. And we have keeping a positive 1 coulomb charge here. So we have two positive charges there. So this positive 1 coulomb charge will be experiencing a repulsive force due to the positive Q charge. So this force will be acting along this direction. This is the direction of the repulsive force. But at the same time, this negative Q charge will be attracting it. So this is the direction of the negative charge. Even though their magnitudes are equal, they are acting in two different directions. That is the problem here. It is along the equatorial line. Their directions are not opposite. If the directions are in the opposite directions, we will be able to find the resultant very easily. If both of them are acting in the same direction, the process was very easier. But unfortunately, both the forces are equal in magnitude, but they are acting in the different directions. So we have to go for the resultant by using the vector formula, or that is little bit complicated because we have 1 by 4 pi epsilon 0 q divided by r square plus a square, the big terms of a square plus b square plus 2ab cos theta. That process will be slightly lengthy. So we are going to derive this in a more easier way. Let us see. Again, this figure. Okay. Okay, I will be writing here the charges. This will be the negative Q charge. This will be the positive Q charge. Okay, the positive Q charge will be repelling, and that's why the direction has shown like this. Okay, so I have kept a unit positive charge there. So this is the direction of the force due to the positive Q charge. This is F or E positive Q or F positive Q, whatever it may be, we can write there. Now, what will be the negative charge doing? It will be attracting. So this is the direction of the E negative Q. So there is an angle. This is the angle between the two forces. It will be difficult to calculate that angle directly now. So what we will do is we are going to split this forces into its components. So this is the force which is acting in this direction. I'm going to split it into two components. One along this direction, the equatorial line, and another one along perpendicular to it. Or I am going to resolve this vector into its rectangular components. You know what are rectangular components of a vector? The components of a vector which are mutually perpendicular to each other. Okay. Let us see what are the components. So this will be one component, and this will be the other component. This is the component of this repulsive force. So if you see the parallelogram law of vector addition, this will be the resultant of this one and this one. Okay, I think it is clear. So this is one component. It will be acting along this direction towards left, and the other will be acting towards up. Now again, we can split this one, the force acting in this direction, into its components. Let us see. So this will be the component which is acting downwards. It will be not acting upwards because this is the resultant. So this is one component, and the other component will be in this direction. So you can see both these forces have the same magnitude. So their components, one is acting in the upward direction, and this will be acting in the downward direction. But this component, the component which is parallel to the axial line, will be acting in the same direction. So now we can see how to find this component. So if this angle is theta, let me see if let me say this angle, I will mark it there. This angle is theta. So this angle also will be theta. This one also will be theta. So what about this component? This will be E cos theta component. This will be E sin theta component. Again, the E cos theta component of this one also is acting in the same direction. You have seen it. This is the E sin theta component. What is the these angles are same, all angles are theta, and you see what is the value of E? E is the, whether it is a positive charge, E will be equal to 1 by 4 pi epsilon 0 q by r square plus a square, that we have seen. E will be equal to 1 by 4 pi epsilon 0 q by r square plus a square. So when you add these two, what will happen to these two components? So this is similar to writing two vectors like this. One is vector r1. I am writing it in components. Vector r1 is equal to xi cap plus yj cap. and vector R2, another vector which has the same x component, but y components are acting in the opposite direction. So vector R1 is xi cap plus yj cap. Vector R2 is xi cap minus yj cap. So when I find the resultant of these two, or when I find vector R1 plus vector R2, this will be, these two components will cancel each other. This, because it is positive y vector j, this is negative y vector j, unit vector j. So these two will be cancelling and the resultant will be only 2xi cap. So what happened to the y component? The y components cancelled each other, but the x components are added up to give the resultant vector. Now we can come back to our situation. This is E sin theta. E is 1 by 4 pi epsilon 0 q by r square plus s square. This is E sin theta. Again, E has the same value, but E sin theta, this E sin theta is acting upwards. So, and this E sin theta is acting downwards. So we can put a negative sign here. We can put a negative sign. So when you add these two vectors, these components will be cancelling each other. The perpendicular components will be cancelling each other, but the horizontal components will be added up. So the resultant electric field, when I calculate the resultant electric field, it will be equal to, E is equal to, only we have to consider the cos theta component. So one is E cos theta, another one is E cos theta. So it will be 2E cos theta. Okay, the resultant will have a magnitude equal to 2E cos theta, and in which direction it will be acting. So this is the negative charge, this is the positive charge, though this is equal to vector P. Vector P is acting in this direction. So this electric field will be acting in a direction opposite to vector P. It will be opposite to the direction of the dipole moment. So it will be acting towards the left, since the dipole moment is acting towards right. Now, to get the total electric field at P, just we have to substitute the values of E and cos theta. Substituting the values of E and cos theta. Okay, we can substitute it. So what is E? E is equal E. So this is a total force. E is equal to this. E is actually 2 into E is 1 by 4 pi epsilon 0 q by what we have in the denominator r square plus s square. Magnitude of both these into how to find cos theta. Now cos theta we can calculate with the help of trigonometry ratios. This distance is r, this angle is theta, this distance will be a, and this distance is root of r square plus s square. So what is cos theta from this right triangle? Cos theta is equal to adjacent side by hypotenuse. Adjacent side is a divided by square root of r square plus s square. So this is the value of cos theta. So when you substitute these two values, our answer will be electric field is equal to 2 into 1 by 4 pi epsilon 0 q divided by r square plus s square into a divided by r square plus s square, the whole raised to 1 by 2 or root of. So you can multiply them, and your result will be what you will get at the end. I will write it here. So we have the expression for ES is equal to 1 by 4 pi epsilon 0. A2 is the 2QA divided by the denominator we have r square plus s square and square root of r square plus s square, which is r square plus s square, the whole raised to 1 by 2. So when you add them, we can write it as 1 by 4 pi epsilon 0 into what is this 2QA, or it is Q into 2A, no difference. It is P, the dipole moment, divided by r square plus s square. This power is 1. Here it is 1 by 2. You will be getting 3 by 2. So E will be equal to 1 by 4 pi epsilon 0 P divided by r square plus s square, the whole raised to 3 by 2. Yes. So we will get the resultant, the electric field on the equatorial line will be this one. And you have already seen the magnetic field, electric field on the axial line. That is 1 by 4 pi epsilon 0, 2P divided by r square minus s square, the whole square. So we got the expressions for both electric field on the equatorial line and axial line. So if you represent it as a vector, how will you write it? Vector E with respect to P. I told you that this P is acting in this direction on the axial line or anywhere, but the electric field is acting in the opposite direction. So how do you write it as a vector? We can write it in two different ways. P divided by R square plus A square the whole raised to 3 by 2 with a negative P cap. Multiplying with a unit vector will not change the magnitude. Or P into P cap can be written as vector P. Or it can be again written as 1 by 4 pi epsilon 0 into negative P by R square plus S square the whole raised to 3 by 2. So when you keep the dipole in a particular place, and if you calculate the electric field along the equatorial line, always its direction will be opposite to the direction of the dipole moment. The electric field is always directed opposite to the direction of the dipole moment. Okay. Now, this is the explanation of what I have written there. You can see this already. I have explained all this. Now we are going to a concept of a short dipole. So a short dipole is the distance between the dipole. The distance between the two charges is very less. A short dipole refers to two charges are very close to each other. So A is very, very less. So what will happen to the electric field at a point? So this is the expression for the electric field due to A. This 1 by 4 pi epsilon 0 2rp by R square minus S square the whole square. In the case of a short dipole, it will be the value of A is very, 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 very small in comparison with the R. When A is a very, very small quantity like 0.1 centimeter or 0.1 meter square, sorry, not centimeter, it will be in centimeters or millimeters or nanometers. When A is a very small quantity, its square will be again very less. So A is very small. So we can neglect A square in comparison with the R square. So this term will be becoming almost 0. So what happens? This condition we can apply. So R square minus A square is almost equal to 0. We can neglect the value because A square is subtracted from R square. A square is a very small value. So when you subtract a very, very, very small value from a large value, we can neglect this. So we can write it as R square the whole square. So we will get R raised to 4. We have an R here. So these two will be cancelling and the electric field intensity will be 1 by 4 pi epsilon 0 to P by R cube. So this is the expression for the electric field due to a short dipole at a point on the axial line. It is 1 by 4 pi epsilon 0 to vector P by R cube. And we can see what will happen in that equatorial line. Again, we are considering the same argument. A is a very small quantity and its square will be again very, very small. And when it is added to R square, we can approximate it to R square. So we can neglect this value. So what we will get? R square, the whole raised to 3 by 2. So in the numerator, when you neglect the value of A, we will get R square, the whole raised to 3 by 2. So these two will be cancelling and it become R cube. And our result will be negative 1 by 4 pi epsilon 0 into vector P by R cube. Vector P divided by R cube. Okay, this is the expression for the electric field at a point on the equatorial line. So let us have a comparison of these two in their magnitudes. So the magnitude of the electric field at a point on the axial line at a distance R was given by 1 by 4 pi epsilon 0 P by 2P by R cube. It is for a axial along the axial line. So if you consider a point on the equatorial line, the expression is 1 by, I am writing only the magnitude, 1 by 4 pi epsilon 0 P by R cube. So what you can conclude? The electric field at a point is on the axial line, which is at a distance R is 1 by 4 pi epsilon 0 2P by R cube. At the same distance on the equatorial line of the same electric dipole, it is 1 by 4 pi epsilon 0 into P by R cube. So what's the relation between these two? If you multiply this electric field at the equatorial line with 2, you will be getting the electric field at the axial line. So this EQ multiplied by 2 will be equal to the electric field on the axial line. So we can conclude electric field at a point on the axial line is equal to double the electric field due to the same dipole at a point on the equatorial line at the same distance from the center. So these two are related like this. And this equation is applicable only for a short dipole. It is not applicable for all dipoles. When we consider very short dipoles, this equation is valid. Okay. So that's all about our first portion. Now we will move to the next. What will happen if you keep a dipole in a uniform electric field? What will happen to a dipole when it is kept in a uniform electric field? Let me share it. Is the new slide visible to all of you? Okay. So let us consider a dipole which is kept in a uniform electric field. So these are the electric field lines which are representing a uniform electric field. It is in a, all these lines are parallel to each other and equidistant. So let us consider a dipole consisting of negative Q and positive Q charges kept like this. And 2A is the dipole length and P is its moment. And let this dipole moment P makes an angle of theta with the direction of the electric field. The angle between the direction of the dipole moment, which is marked there, let it be vector P. The angle between vector P and vector E is theta. So it is kept in a uniform electric field. Now we have to calculate what is the total force experienced by this dipole. And also we should find what is the total torque experienced by it. So let us go for the total force. So this dipole is made up of two charges. One is positive Q and the other one is negative Q. So both these charges, they are kept in the same electric field. So they will experience a force. So let us see what is the force experienced by the positive Q charge. I have shown the direction and this will be along this direction. QE will be acting in this direction. I think you may be recalling the fact when a positive charge is kept in a electric field, it experiences a force. If the charge is Q and the electric field is E, the force will be QE and the direction will be, I have mentioned, same as the electric field. When the charge is positive, the direction of the force will be same as the electric field. So QE will be acting along the same direction. So what will happen with the negative charge? That also will experience a force, but it will be experiencing a force in the which direction? A negative charge will experience a force in the opposite direction of the electric field. So this is the direction of the force acting on the charge negative Q. So what is the total force acting on the system as a whole? There are two forces. One is, let me call it as vector F1, or the charge acting on the positive charge. Second one is the force acting on the negative charge. That will be the total force. Vector sum I have to consider. But how to find the vector form? QE is acting in this direction. So QE, if I take the direction of QE as positive, so I can write it as Q vector E. Same as the direction of E plus, what about E negative Q? Its direction is opposite to the direction of E. So I can write it as negative of Q vector E. So what will happen if you add these two vectors? Both of them have the same magnitude, but they are acting in the opposite direction. These are two vectors which have the same magnitude. They are acting in the opposite direction. They definitely their sum will be, or resultant will be 0. So what do you mean by that? A dipole as a whole will not experience any force in a uniform electric field. So if I keep a dipole in a uniform electric field in any direction, in any orientation, that dipole will not experience any total force. The total force will be 0 in that case. Now, what is the speciality of these two forces? So this one is acting along this direction, and this force is acting in the opposite direction. Their line of actions. This is the line of action of the first force. This is the line of action of the second force, and they are the forces are equal in magnitude, their directions are opposite, and their line of action is parallel to each other. What's the name given to such a force? Some of you might have heard it in 11th class. Two forces which have the same magnitude, opposite direction, but they are having their line of action parallel to each other. Such a force is called, what is the name of such forces called? Couple. And what the couple will do, the couple will constitute a torque that you have learned in the 11th class. To open the lid of a bottle, we need two fingers. We will apply two forces on the lid, one in one direction, other one opposite to it, but line of actions will be parallel to each other. So we are going to find the, what is a torque? So here also we have in this situation, we have two forces. One is QE and another one is negative QE, and both of them are acting in the opposite direction and their lines of action are parallel to each other. So let us try to find the torque acting on this. So how to find the torque? We have learned the expression for the torque in the lower classes. In 11th class, we have seen the expression for the torque. Okay, so I have the two forces. One is, I am writing the magnitude here once again. It is QE. Other one is also is positive QE. F1, F2 is negative QE. And the torque is, the magnitude of the torque is given by force into the perpendicular distance between the two forces. That is you have learned it in the last class. Sorry, not in the last class, in 11th class, you have learned the torque acting is, torque by a force is obtained by multiplying one of the forces with the perpendicular distance. So what is the perpendicular distance between these two forces? The perpendicular distance between the line of action of the two forces, we can calculate it now. How to find this distance? So this angle is theta. This angle also will be theta. This is 2a. So what is, how to find this distance? Using trigonometry. So we know that sine theta, sine of angle theta is equal to the ratio of, mathematics students know this very well. Others, the sine ratio you have learned in 10th class, the ratio of opposite side to the hypotenuse. So it will be, I am just calling this as, this is A and this point as B. So the length is AB divided by, that is the perpendicular distance, divided by 2A. So AB, the perpendicular distance is equal to 2A sine theta. The perpendicular distance between the two forces is 2A sine theta. Okay. I think it is more clear now. This is the perpendicular distance. I have calculated sine theta. Sine theta is equal to, this is AB. AB divided by 2A, or AB is equal to 2A sine theta. So now we are in a position to find the torque. Torque is equal to F, one of the forces, into AB. So we know the value of F. What is F? Q into E. Magnitude is QE. Sorry, it is QE. And the perpendicular distance is 2A sine theta. It can be written as 2A QE sine theta. This 2AQ is called P. So this is written as PE sine theta. So that magnitude of the torque is given by PE sine theta. So again, let us see little vectors. We have seen a vector whose magnitude is AB sine theta with respect to vector A and vector B. Which vector has this magnitude AB sine theta? You have learned two types of products of vectors. One is dot product and other one is cross product. Actually, the cross product of two vectors, vector A and vector B, has a magnitude equal to AB sine theta. So if you see AB sine theta in vector form, we can represent them. If A and B are vectors and theta is the angle between them, then AB sine theta is the magnitude of vector A cross vector B, or vector A cross vector B will be equal to AB sine theta. Here we have two such cases. One is vector P, other one is vector E. and we have a vector whose magnitude is P sine theta. Definitely, the torque tau in vector form, I can write it as torque tau is equal to what it will be? PE vector, sorry, it is P sine theta in the form of vector. We can write it as, I will write it here, vector P cross vector E. Vector A cross vector B is AB sine theta. The magnitude of A cross B is AB sine theta. Therefore, similarly, we can say, since the magnitude of tau is P sine theta, vector tau must be vector P cross vector E. So this is the total torque experienced by a dipole in a uniform electric field. So we can conclude one thing: when a dipole is kept in a uniform electric field at any angle, it will not experience any resultant force. The resultant force acting on it will be zero, but at the same time, it experiences a resultant torque, which is given by AB sine theta. So can you tell me when this torque will become maximum and when it will become minimum or zero? Under what condition this torque is maximum and under what condition this torque is minimum or zero? A and B, so this P and E, they have their own magnitudes, they won't change. We have a non-zero values of P and a non-zero value of E. Then we can consider different orientations of the dipole in uniform electric field. Okay. See, what is the speciality of this orientation? Yes, Pratyusha has given the answer. What is the speciality? In this case, the electric field is acting in this direction and the dipole moment, this is a negative charge and this one is the positive charge. This is negative and this one is positive. So this is the direction of the moment vector P and this is the direction of electric field. They are acting in the same direction. That implies in this case, theta is equal to 0 degree. So what is the torque? Magnitude of torque is equal to PE sine 0. All of us know that sine 0 is 0. So this torque will be equal to 0. Under this condition, the torque will be 0. And this can happen in another orientation also. If this is negative Q and if this is positive Q. So P will be acting in this direction and E will be in the opposite direction. Again, theta will be equal to 180 degree. And again, we know that sine 180 is equal to 0. So this torque is also equal to 0. So under these two conditions, the torque will be 0. If the dipole is orienting parallel to the electric field or they are anti-parallel. If it is parallel or anti-parallel, we can see that the torque will be 0. Now, when it will be maximum, again, we can use the property of sines. If the orientation is like this, if this is the orientation, what is the difference here? This is vector P. Vector P is acting in this direction and E is acting in the opposite direction. And the angle between them is now 90 degree. What is the torque in this case? PE sine 90. It will be equal to PE. Or it will have the maximum value. We know that the sine of an angle is maximum when the angle is equal to 90 degree and the maximum value of sine is 1. Positive 1 is the maximum value of sine and the torque will be maximum and it will be equal to PE. And I have mentioned two cases here. When the torque acting on a dipole in a uniform electric field becomes 0 and when it becomes maximum. Both the cases is important. Now, we are going to derive the expression for the potential energy of a dipole in an electric field. I think my allotted time is almost over. So let me go to the next slide. I'm not going to details of this equation. We can derive the equation will be PE cos theta 1 minus cos theta. This is a work required to rotate a dipole from an orientation theta 1 to theta 2. So initially it makes an angle theta 1 with the electric field, and finally it is rotated to another angle theta 2. So to rotate a dipole in an electric field, we have to do some work. The agent who is rotating has to do some work. So when it changes its orientation from one angle to another, some work is done by the agent. So that much work done is stored in the dipole in the form of an energy, and that energy is called its potential energy. So when you rotate the dipole from an orientation theta 1 to theta 2, the change of its potential energy is given by PE cos theta 1 minus cos theta 2. So this is the energy or the work done or the energy achieved by a dipole when it is rotated from a position theta 1 to theta 2. Now we can make the value of theta 1. Initially, if it is orienting perpendicular to theta 1 is pi by 2 or it is 90 degree. Initially, it is perpendicular to the electric field, and theta 2 is let us say any angle theta. So what I am doing here, I am rotating this dipole from a position where the torque is maximum, that is pi by 2. The cos pi by 2 cos theta 1 will be 0. So 90 degree, it is making an angle of 90 degree or pi by 2 degree in the initially, and it is rotated to a position where it makes an angle of theta. This is the case. This angle is theta. Initially, it was like in this way, so that the angle was 90 degree. So I am rotating this dipole from this orientation to the given position. I am rotating it like this. Oh, so what is the work done for that? Just substitute the values of theta 1 and theta 2. Substituting the values of theta 1 and theta 2 in this equation, you can say the energy gain will be equal to U is equal to PE. It is cos theta 1 is cos pi by 2 minus theta 2 is theta. So cos pi by 2 minus cos theta. So cos pi by 2, what is the value of cos 90? It is 0. So this will be equal to negative PE cos theta. What is this? How this negative sign? Because 0 minus cos theta is negative. So energy will be negative PE cos theta. So this is the energy acquired by a dipole when it makes an angle theta with a given electric field. Now, so far we were discussing with about the discrete charges. A point charge I was considering, and some 2-3 point charges are kept here and there in space. Now the charges can be distributed in different ways, so that they are called the continuous distribution of charges. So we can distribute charges in 3 different ways. The first one is a linear charge or linear distribution. So we can arrange the positive charges like this. So dq charges are arranged over a length dl. Or we can simply say q charges are arranged over a length L when you say about a large line of charge. So this arrangement is called a line of charge. So total charge on the line is Q and the length of the charge distribution is L. So if I find the ratio of this total charge to the length, what does it represent? The total charge divided by the length of the line over which this charge is distributed. So this ratio will give you an idea about how much charge is distributed in a unit length. So I am dividing the total charge, that is this much is the total charge and this much is the length. So it can be either dq by dl or we can say q by l. And this is called the linear density of charge. It is called the linear density of charge. So we can conclude when we distribute charges over a line, we are going for a linear density. That means charge distributed over unit length. Now, what is the second case? This is a distribution over a line. It is called a line charge or line charge distribution. Now we can go to the second distribution. What will come after a line? We can consider the area. The charge can be distributed over an area. If this is the total area, let me, we will denote the surface area as S in our case, or simply A. We were using A initially, but now we will use, since it is a surface area, I'm using the simple S. So here, if dq charge is distributed, dq is a small quantity of charge. It is distributed over an area ds. So the ratio of charges to the area. I'm considering the ratio of charges to the area. So it will be ds divided by dq divided by ds, and this is called, or if q charge is distributed over an area S, it is called q by S, and this is called the surface charge density, since the charge is distributed over an area, and it is denoted by the letter. This letter is called sigma. So whenever we consider some distribution of charges over a surface, like charge distributed over the surface of a sphere or charge distributed over a plane, we will go for the surface density, because charge is distributed over a surface or area. We are dividing the charge with the area, and it is called the surface charge density. Now, another possibility is that the charge can be distributed in a volume. So here I can, you can see a volume or a space whose volume is dV, and the charge dq is distributed throughout this. Now, we will call this called the volume charge density, or simply charge density. I'm going to wind up now, and the density rho will be equal to dq by dv. Hello, sir. Time. Okay, I might. So in this case, the charge is called the volume density of charge, and it is q by v. So these are the different cases of distribution of charges. Charges can be distributed over line, surface area, or in volume. So this will be useful when we go for Gauss theorem. When you learn about the Gauss theorem, this charge distribution and the densities are important. In the next classes, we will make use of this. I think my allotted time is over. I think you understood whatever I taught to you, and you can raise the queries by using the chat box, or you can send it, and I will be answering your queries in the evening session. And in the afternoon session, we will be dealing with problems, especially the problems which are some competency-based problems, and some multiple choice questions, assertion, reason type, and some hard questions, of course. We will be dealing with problem solving in the afternoon session. Okay, thank you very much. Have a great day. Thank you. I am signing out.